this session of the morning. Before we really leave it to the first speaker of this session, just let me say just a couple of words. I owe a lot to Sergio Caracciolo, as many of us have already said. Among the many teachings, just let me single out one which really stands out for me, which is this idea of a scientific problem that you choose, and it keeps you company. It's something that stays with you when you go about your day. And this idea, together with, of course, with the passion for curiosity-driven research, is really something that I cherish. It's a lovely and powerful idea. So I join everybody else in saying thank you very much, Sergio. So I'll leave it to the first speaker of this session, who is Stefano Zapperi. He's gonna talk us about crackling noise.
Okay, so thanks a lot. I see. Sorry. There was an echo. Sorry, my computer was sending me back what I was saying. So thanks a lot for the invitation. I'm very happy to be here to celebrate Sergio, who is my next door colleague. So I'm happy to see him here. Last years, we didn't see each other so much because each of us was, for various reasons, including the pandemics, we're not very much in the office. So let me start, let me first see if I can start. To start, let me say a few words about Sergio. So I met Sergio around 15 years ago when I was actively trying to go to Milan, and I was in Rome at the time, and Rome and Milan are two separate cities, so it's not so easy to find connection and so on. And I would say that Sergio was really a fundamental person for me moving to Milan. He was always very welcoming. He hosted me whenever I would visit. And then there was even, we did a project together in the early days. He proposed that we could co-advise a student, Massimiliano Baraldi was a student. And so we worked together in this problem about growth and form of melanoma cell colonies, where we looked at some experimental data from Caterina Laporta in Milan, and we tried to construct a statistical physics model to describe their distribution, their shape. We finally found out that the shapes was very well described by the Eden model, so the KPZ universality class, and then we published a paper in Journal of Statistical Mechanics, Theory and Experiment, which you can find here. And this is the physics department. It's more or less where we sit close to each other now, after I joined the physics department in 2015. So I would like really to thank Sergio for his support over all these years. So I'm very happy to be here celebrating his birthday. And so now let me go to the topic of my talk, which also spans a very long time. So I've been active in this field on and off for the last 30 years. And the idea is to study this crackling noise. So what is crackling noise? There are many examples of crackling noise, and crackling noise is essentially a noise that has a lot of crackles. So intermittent burst followed by quiet period, and then intermittent burst. And there are many examples in nature. Fracture, acoustic emission in fracture, in crystal plasticity, the acoustic emission when you open a lung that has been degassed. Earthquakes is another example of crackling noise. So this, if you just record the acoustic activity during earthquake, is crackling sound. Friction of granular media, the Barkhausen noise, and I will discuss more about it, which is noise emitted by magnets. Stock prices also really look quite similar. And in biology, again, neuronal activity is another example of crackling noise. So there are several examples, and the common feature of all these systems is that there is a power law distribution of some sort, typically of the amplitudes. There are some non-trivial spectral properties and so on. So there is a very general type of noise. And the question is, how can we understand it? And this focus on crackling noise started more than, let's say now, 35 years ago, with this work by Bach-Tang and Wiesenfeld, who proposed this concept of self-organized criticality. And the idea was illustrated by a simple model, just a toy model. You have grains, and then you add grains, and you can imagine that there is a height profile with variables z, z, and then at each when the system is quiet, you add grains to the table, and then there are rules. And the rule is that when the height overcomes a certain threshold, we call it ZC, then there is a toppling event. And here I illustrate one in a particular case in which ZC is equal to 2. So 2 grains become unstable, and then they get transferred to the neighbors, the 2 grains. And of course, you can change the rules differently. So you can change ZC and so on. And then you see that when 2 grains, for instance, in this kind of event, 2 grains are transferred to the neighbors. One neighbor has already one. So, okay. So one neighbor has already a grain here, and he gets another grain on top. So this will create an avalanche, so toppling avalanches, and so on. So this is the dynamics. And the avalanches can be very complex. And this is a big avalanche, where in gray, with the grayscale, I highlighted the number of topplings of each side. So just for a single event. So they can be very large and so on. And then there are several interesting issues. There are stochastic SANDPILES like this one. You pick up 2 directions at random and you throw the 2 grains. And I will mostly talk about stochastic SANDPILES. But there are also some called abelian SANDPILES. And abelian SANDPILES have like ZC equal to 4. And so it's deterministic. You just throw the 4 grains to the 4 neighbors, and they have some interesting mathematical structure. And Sergio also contributed in elucidating the structure of these abelian SANDPILES. So there is a very rich literature on that. So, but I will work mostly on the stochastic ones. And then the last point is that grains exit from the boundaries. And then when everything is stable, you start again. So this is a sort of toy model for avalanches. And you can measure statistical quantities, and typically one defines a pulse. So this is the number of topplings event, call it V in this case. So the number of sites that are active as a function of time, and then this is an avalanche. And then ends to when it stops, then there will be another avalanche. And typically one measures the duration of this event and the size, which is the area under the curve, or just the number of topplings. And then if you look at the size versus time, you get this nice crackling noise. No? So it's very similar to the experiments, at least qualitatively. Then the interesting stuff is that there are scaling laws. Typically, the distribution of avalanches is a power law like this, and it has a cutoff that scales with the system size. Distribution of duration is also a power law. You can measure the average size as a function of duration, and this is also a power law, and you can find scaling relations. And power spectrum is also a power law with a non-trivial exponent that is actually equal to this exponent here, and this was shown first by Jim Setna 20 years ago. And then what is more important is that not only there are scaling exponents, but there are also scaling functions. So this F, this G, and also an interesting one that was also introduced by Jim Setna, which is the average shape of the pulse. So it's the excursion, the average excursion of this pulse. And these all these exponents and scaling function are supposed to be universal. At least there should be some universality classes describing them. And now the question is, can we really use this knowledge to understand some of this experimental crackling noise that we have shown in the first slide? And so I would say that there were 3 questions here at the outset after all these initial years on this avalanche behavior. And crackling noise is, what kind of critical point are we talking about? So we have scaling function exponents and possibly universal, but what kind of non-equilibrium critical point are we talking about? And why is it critical? So why it happens that all these nice experiments are critical? So why should they be? No, there's no particular reason. And when are they critical? So are they really critical? Are they quasi-critical? How close are we from the critical point? And then is all this toy model and so on that we can maybe understand theoretically relevant for real crackling noise? So is it just a coincidence? They look similar and so on, or there is something deep that we can understand. So, and this was with the program of research in the past 20 years. And I think we solved most of these questions, and I will give you a glimpse of this and in the coming slides. So first of all, to understand SANDPILES, it is useful to change a little bit the model and say, because we want to understand the phase transition underlying these SANDPILE models that have this scaling behavior. And the simplest way is to set the driving rate to 0 and the dissipation rate to 0. So now we close the boundaries. So once you have some sand inside, some grains inside, they remain inside, and we don't drop any grains. So now you have the only control parameter you have is the number of grains in the system. No? And then you can measure this, like the average height of the sample is the number of grains in the system. And turns out, if you study this model, it has no avalanches anymore, because of course there is either the system is stuck, there are no sites above the threshold, and so nothing happens. So you have so-called absorbing state. So once you're there, you never move, or you're active. So there is some activity. So there are a few sites that are, or maybe a lot of sites that are above the threshold, and so there is an avalanche that goes on forever, or some activity that goes on forever. Of course, in a finite system, it will die out eventually, but you can think this as a absorbing state phase transition. So a state where you never exit from, and a state where you go on forever. And there is a critical point. And these kind of absorbing states are very common in non-equilibrium physics, in equilibrium statistical physics, and has been studied very in depth. So we could use a little bit of the knowledge about this system to understand this critical point. So now what happens when you have now a driving rate, H, and the dissipation rate? So now you add grains and you also dissipate them. Okay, for simplicity, we can say that dissipation could be not only through the boundaries, but with a small parameters epsilon in every side. So sometimes grains disappear. Okay, this is just a variant of the model that is equivalent to the boundary case. And so you can write an equation of motion for the height, for the average height, which is just what you add minus what you remove plus what is diffusing through the avalanches. And it's diffusing through another field, which is the density of active sites, because only sites that are active can diffuse. No? The dead sites, they don't diffuse. And now this equation tells you that on average, the activity is just H over epsilon. No, it just takes the average of this equation. And now what happens when you look at this equation? Well, it tells you that if you are in the stack phase, there are no active sites here. And so this just tells you that you will increase the height. No, zeta will increase. And it goes towards the critical point. On the other hand, if you are in an active phase, so there is a lot of this activity here, but you also dissipate. And so the height will decrease. And so at the end, these dynamics here will keep you around the critical point. So back and forth. But now, when are you really critical? Well, you are critical when you go very slowly. So you add grains very slowly, and also you dissipate very slowly. And the limit should be taken so that this value goes to 0 and doesn't diverge. So you really go to the critical point, which is 0 activity, but you go it slowly. So that's basically the mechanism by which you can understand this, why this SANDPILE is critical. Now, can you do more than that? Yes, and since we are in statistical field theory workshop, I mentioned that we derived now many years ago a field theory for this process, which is written here. So it's a bit complicated, as a nonlinearity here, and also some noise that is of the type of the directed percolation type noise. So, and this equation we could study a little bit, but not really solve. So we understand some features, and simulation show that it's really describing stochastic SANDPILES, but there was not much to say about it, not much to say. So it rested there for more than 15 years, actually 17 years. And then finally in 2015, so Pierre Ledoussat and Kay Wiese managed to do a functional renormalization group of this equation and get epsilon expansion and find, okay, upper critical dimension was known, but find all the critical exponents, and they match very well with simulation. And one critical aspect of this functional renormalization group was that this field theory maps into another field theory that describes another problem, which is a problem, another non-equilibrium phase transition with quench disorder. And let me tell you something about that. It's the DEPINNING transition. And this is the equation for the DEPINNING transition. It describes an interface. The interface is pushed through an array of pinning points or a disordered random field, wherever you want to do it. And then the equation of motion of the interface is this one. You have an external force, you have some interaction kernel, which could be just a Laplacian, plus you have a quench disorder. So, and this makes the equation nonlinear because it depends on u here. And then you have a thermal noise if you want. And this DEPINNING transition at t equals 0 has this, again, non-equilibrium transition with a critical point, and then velocity is the order parameter. And very similar to the phase diagram of the SANDPILE. And of course, no, that's no wonder, because really they are the same. They are described by the same field theory. And when you add temperature, you get a smooth out of the transition. So now, how do you self-organize this interface? So make it as a SANDPILE. So what you can do is, instead of pushing at a constant force, you attach the interface to a spring, and then you pull the spring at constant velocity. This will give you a force that is just the spring constant minus position of the endpoint of the spring minus the position of the interface. And when you do that, you have the same behavior, so you're coupled. And of course, if you want to go really to the critical point, you have to make the spring stiffness go to 0 and the velocity also go to 0. Okay, but slowly go to 0. So it's exactly the same thing. So in this will now allow us to define a few classes of crackling noise. So there is the tune criticality type of noise, so where the force is constant, whatever the force is in the system under study, and you will have a power law distribution with a cutoff that depends on the distance from the critical point, classical criticality. Then you have the self-organized variety, in which the force is some sort of spring-mediated pulling. And there are experimental systems I will show where this is quite relevant. And now, again, you have a power law, and now the cutoff is replaced not anymore by a cutoff that depends on the distance from the critical point, but by something that depends on the spring stiffness. So the spring stiffness still is a control parameter and will set up your cutoff. So if it's very small, then the cutoff will be very large. And finally, there is a third class, which is a force that is pushed at constant rate and no spring stiffness. And in this case, it's interesting because you integrate over all these forces, and at the end of the day, you get a different exponent with no cutoff, which is just the sum of the tau exponent and the sigma exponent. And all these three classes, you will see, have counterparts in real crackling noise. So let's take one example. This is a nice example because it has both a couple of classes already. So you can have case B and case C. So Barkhausen noise is the noise you observe in looking at the magnetization of ferromagnets. And it's quite generic for any ferromagnet. And essentially, the hysteresis loop has jumps. So if you take the derivative of the hysteresis loop, just you measure typically what you do, you measure voltage around the coil around the sample, then you get this kind of noise. And now you see that there are two possibilities. One is that you measure the noise all along the curve. And when you do that, you see that you start small and then you get big. No, the average noise goes up and down. And in this case, it's clearly a case where you're sweeping your system towards the critical point or the instability. And indeed, the exponents are large, so around 1.7, the exponent. And the other case is when you focus on a small region here, where the signal is stationary. And in that case, you get an exponent that is smaller, 1.33. And by the way, this exponent matches perfectly with the DEPINNING transition exponent. So it's really quantitatively correct. And what is the spring here? So we said that we could get the case B where you had a spring. And the spring here is given by this demagnetizing factor. So essentially, the effective field felt by the domain walls is the magnetic field, which you ramp up from outside, minus a term that corrects for the demagnetizing field. So every magnetized body has a counter field inside, and essentially these flux lines. And now Gianfranco Durin made nice experiments in which he could control this KD just experimentally. Typically, you can play with the aspect ratio of the sample or add a magnetic yoke, is called. So try to close the flux, but not completely. So you can really fine tune it. And well, what you get is a cutoff that depends on K, and the scaling function matches exactly the one predicted by the theory. So you really can pinpoint that this is the mechanism for this case. You can go further with this noise. You can measure the excursion of the noise, this famous avalanche shape proposed by Jim Setna. This is a work that we did together, and again with Gianfranco Durin, who did the experiments. And you can see that you can perfectly get the theory matches perfectly with the experiment, not only for the scaling function at criticality, but also from the deviation from critical behavior. So again, theory of critical phenomena does not only predict exponents, but also entire scaling function, and you can measure them experimentally. So that's the beauty about critical phenomena and theory, renormalization group theory. Another example, in this case is case A, so tuned criticality. This is the case of a crack front. So you have experiments done by Knut Malloy and Stefan Santucci, in which they have a plexiglass plate, and they pull it, and they observe the crack front line. And the crack front line, they make jumps when you pull it. And the force that pulls them is the so-called stress intensity factor, which is basically a measure of stress projected on the crack. So it's just from theory, linear elastic fracture mechanics. And there are interactions that come from the elasticity. And in this case, again, here we have at the same time the red dot are the theory, the model, and the white dot are the experiments, and you can collapse into the same universal scaling function. So again, you can really explain all the experimental behavior with data collapse. Another kind of crackling noise is that observed in microplasticity. So you have this micropillar of crystalline micropillar. In this case is nickel, but you can do it with any material, and you compress them. And if you look at the curves, stress strain curves, it has all these jumps. And if you measure the jumps, they are power law distribution. This was done by the group of Dimiduk in 2006, but then after that, there have been many other experiments. And here, what is the physics? The physics is dislocations. So you have a lot of interacting dislocation in the crystal, and when you deform, the dislocation move and get pinned. No? And so we studied this by simulations, and we could check the crackling noise from the simulation. And now, if we want to go back to the classification, what kind of criticality is this? This is again case B. So you pull by spring. And what is the spring here? It's the sample itself, and it's so-called strain hardening coefficient. So when you deform plastically a sample, ideally it should be flat, so no stress increase when you increase the strain. But since you're generating new and new dislocation, this dislocation acts as spinning centers for the other dislocation, and so it will give you a stress, no? A back stress on your sample. And this is something that you can measure, and then you can use it to collapse all your experiments. These are the experimental data and the simulations into a single universal master curve with a formula that you can derive analytically. So again, you can really, using this knowledge about the kind of criticality that you expect, you can understand some experimental, fairly complex experimental behavior. Now, let's come to another example, and then I will end, don't worry. This is glasses. Okay, glasses is particularly interesting, and there is active work still going on to understand them, in particular the deformation of glasses. And when you deform a crystal, you know that dislocation will play the role of relevant degrees of freedom. In glasses, there are no dislocations. But it turns out that there are some localized shear transformations, so some region that deform plastically. And so they are somehow localized. And this you can see from simulation. For instance, here there is a simulation we did with Itamar Procaccia on silica, realistic model of silica glasses. And if you look at it, you see you get this localized rearrangement here in the lattice. And this localized rearrangement, these again silica glasses, have this sort of quadrupolar structure. So it's similar to the strain field that you get when you, to the stress field that you get when you move a dislocation of one lattice spacing. So they look like dislocations in some sense. And so they have this kind of quadrupolar stress field, which you can see here. This is the shear component, of course. This is a tensor, the stress, so it's a more complicated. So it's very similar to the case in which you take a little sphere inside your sample and you deform it into an ellipsoid. And that's what is called an Eshelby inclusion. And so we can use this to create a model for glasses, which has a lot of, is a lattice model, in which each of these blocks is in 3D, actually, in 2D and 3D. Each of these blocks can deform plastically. You compute the stress field using the Green's function, so it's a tensorial, and then you project it and you evolve it. So if you want some more detail, you can look at this paper. And essentially what you find with this model is you can reproduce all the pattern of shear bands that you typically observe in experiments. And these shear band patterns depend on the type of loading. So if it's traction, some sort of shear, or bending, or indentation. So everyone is different. But what is interesting is that the avalanche distribution, so these bursts that come from this localized rearrangement that propagates through the stress, they are all the same, and they are universal. So it's a very strong universality, and you find a unique scaling function for them. So again, this is the power of critical phenomena. Microscopic detail may change, so the shear bands are different, but there are some universal features. And another interesting thing about these glasses is this concept of marginal stability that has been introduced by the group of Itamar Procaccia, and then also worked by Müller and Biar. And the idea is that in glasses, contrary to all the other systems I showed you before, there is some sort of marginal stability. So the threshold to activate one of these, let's call X the stress that you need to activate one of these shear transformation. And now you look, since the glass is disordered, you look at the distribution of these X's. And it turns out that this distribution is a power law at low X. So you have always some sides that are almost unstable. So it's a divergence of stability. So you can always excite the glass with very little work. And this has consequences on the avalanche distribution, which doesn't fit any of these three classes that I showed you. And so it's, let's say, case D. And in this model also we can find it, and it's universal. We find this exponent and also the scaling function for this marginal stability distribution. So that's something that is found in atomistic simulation, but is recovered by our model. So it puts glass into a different class. And final example I wanted to show you is a completely different field. Now these are cancer cells, and they move, but they are actively moving. Nobody's pushing them. They are pushed by themselves, and they're moving on a collagen substrate, which slows them down a little bit. And so what you can see, if you look at the fronts, they have clear avalanches, and here are the avalanches. And again, there is universal scaling in this system. Now we have like 10 types of cell types, and some simulation of an active particle model, and they all fit into a single scaling function, which you can get from models similar to the one we discussed. So this kind of framework works also for very different phenomena, even in the life science. And there are other examples that I don't have time to talk here, like gene regulation, neuroscience, and so on. But it's quite generic, I would say. So what is, just to summarize, since I think I reached the end of my talk, what is the roadmap that we have taken in the past 30 years? So we started from very idealized SANDPILE models, that is certainly not realistic. We developed a field theory. The field theory was shown to be equivalent to a DEPINNING transition field theory, and this provides quantitative predictions for scaling functions, scaling exponents, tuning parameters, and so on. So it gives a broad understanding of the phenomenon. So we can define classes of crackling noise, and then with all this theoretical background, have a look at the experiments and try to be quantitative and make predictions. And so essentially, we can, I think, understand the origin of the observed scaling in experiments, identify the relevant control parameters, predict the exponents, and the scaling functions. And so everything, I think, it fits together. And I would like to thank you for your attention, and also thank all my many collaborators that contributed to this understanding. And if you want to know more, there is a book that just came out a couple of months ago on crackling noise that tells all the story. And since this is Sergio's birthday, I have a copy for him. And with this, I thank you for your attention again.
Thank you, Stefano. We have some time for a few questions. Yes.
So I have a very simple question. So I would like to understand in the first example, when you go from the simple case in which the driving and the dissipation goes to zero, which is a phase transition with a absorbing state, and when you insert the drive and the dissipation, there are non-equilibrium features that sets in, and do you really see the effect of these non-equilibrium features in the field theory that you construct for these class of models?
So the field theory is the same, essentially. Is basically given by two equations. One equation for, maybe I can show. So there is this equation. It's very simple for zeta, and then there is an equation for rho, but rho a, and the equation of rho a. Now I'm lost. The equation for rho a depends on zeta. Now, if you substitute, the first equation is linear, it's easy to solve. You substitute in the second equation, then you get that field theory we got. So it depends on h and epsilon, and you can set them to zero. And so, well, you have a field theory that works in both cases. In the cases where you have h equals 0, epsilon 0, and then z is a constant, zeta is a constant, or it's the same, exactly, it's the same field theory. And so, of course, since it's the same field theory, it has the same exponent and same critical point.
Any more questions? Yes.
So something I didn't get actually. So let's say in the first case you have, like, let's say, an elastic membrane and you pull it.
Yes.
Then in the last case of the cancer cells, you said that this is not an elastic membrane, but it should be more imagine like probably a membrane with active forces.
Yes.
But do you find the same scaling? Because
it turns out that this the same, but why I don't know. So
okay.
So to be honest, I don't know. So it turns out that it's the same exponent as the crack.
But a scaling function.
Also a scaling function. Actually, we used the scaling function that was obtained by a functional renormalization group, and it worked very well. Now, I don't know, maybe it's just an accident, and of course, I mean, there's always a power law with some cutoff. So it's but we use the same kind of scaling function predicted by the Dussal and Wiese, and we put it there, and all the data collapse.
Okay, thank you.
But I have no answer as to why this is true.
Any more questions? No, if no, we can go on. Then let's thank the speaker again. Thank you, Stefano.